This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a research paper focusing on fault detection and diagnosis, FDD, within the engine electrical system of a space launcher. The authors propose a novel approach using a temporal convolutional autoencoder, TCAE, and calibrated classifiers. What are the key challenges in developing robust FDD systems for such a critical application?
The primary challenge lies in the high reliability and safety requirements of space launch systems. Traditional model-based approaches often struggle with the complexity and variability inherent in real-world operational conditions. Data limitations, particularly in fault scenarios, further complicate the development of accurate and reliable FDD systems. Furthermore, onboard computational constraints necessitate efficient algorithms.
The paper highlights the limitations of existing approaches. What specific shortcomings do they address?
Existing methods often rely on manual feature engineering, which is time-consuming and requires significant domain expertise. They may also struggle with noise and variability in operational conditions, leading to false positives or missed faults. Additionally, many lack the ability to handle out-of-distribution data, representing unknown fault types or unforeseen circumstances.
The proposed solution uses a TCAE. Why is this architecture particularly suitable for this application?
The TCAE is well suited for handling sequential data, such as the time series data from sensors in the engine electrical system. Its use of dilated convolutions allows it to efficiently capture both short-term and long-range temporal dependencies within the data, which is crucial for accurate fault detection. The autoencoder aspect allows for unsupervised feature extraction, reducing reliance on manual feature engineering.
The paper mentions the use of histogram-based gradient boosting trees, HGBT classifiers. What advantages do these offer over other classification methods?
HGBT classifiers are known for their efficiency, robustness, and scalability, particularly when dealing with large datasets. Their ability to handle mixed data types and manage missing values makes them well suited for real-world sensor data, which is often noisy and incomplete. They also tend to perform well even with imbalanced datasets, a common issue in fault detection where fault cases are often rare.
The authors emphasize classifier calibration. Why is this crucial in the context of FDD?
Calibration ensures that the predicted probabilities accurately reflect the confidence of the predictions. This is essential for making informed decisions in critical systems like space launchers, where the consequences of false positives or false negatives can be severe. Well-calibrated probabilities allow for a more nuanced understanding of the uncertainty associated with the predictions.
The paper also addresses OD detection. How does their approach handle this important aspect?
They employ inductive conformal anomaly detection, a relatively simple yet effective technique for identifying OD data. This approach leverages the reconstruction errors from the TCAE to determine whether a new observation is consistent with the nominal data or represents an anomaly. They further enhance this with a CESM-based approach to reduce false positives at the trajectory level.
The paper mentions using COSM to limit false alarms. Can you elaborate on its role in the proposed framework?
COSM is a sequential analysis technique that accumulates deviations from a threshold. In this context, it helps to reduce false positives by only triggering an alarm when a cumulative sum of deviations exceeds a predefined threshold. This makes the system less sensitive to short-term fluctuations and more robust to noise.
How does the framework address class imbalance, a common problem in fault detection?
The authors explore several techniques, including threshold moving, which adjusts the decision threshold to account for the different prevalence of fault classes. They find that threshold moving provides the best performance without negatively impacting calibration, unlike other methods such as class weighting or data level sampling techniques.
The evaluation is initially performed on simulated data. What are the limitations of this approach, and how do the authors plan to address them?
Simulated data, while useful for initial testing and model development, cannot fully capture the complexity and variability of real-world data. The authors acknowledge this limitation and plan to validate their framework using real data from a test bench with real valves and electric motors. This will provide a more realistic assessment of the system's performance and robustness.
The paper discusses the use of sliding windows for processing time series data. What are the considerations in choosing the appropriate window size and step size?
The window size determines the balance between capturing temporal dependencies and computational efficiency. Larger windows capture longer range dependencies but increase computational cost and latency. Smaller windows are faster but may miss subtle anomalies. The step size determines the overlap between consecutive windows, affecting the number of samples and training time. The authors experimentally determine optimal values for these parameters.
The results show a discrepancy in performance between the test and test 2 datasets. What accounts for this difference?
The key difference lies in the prevalence of fault cases. The test dataset reflects the class distribution used during model training, while test 2 introduces a significant prevalence shift with a much lower proportion of fault cases. This highlights the sensitivity of the model to changes in data distribution, particularly in fault detection.
The paper mentions several metrics used to evaluate the model's performance. Can you highlight the most important ones and their significance?
Key metrics include OSSI for binary classification, accuracy for multi-class classification, precision, recall, F1 score, false positive rate, FPR, and false negative rate, FNR. These metrics provide a comprehensive assessment of the model's ability to detect and diagnose faults, considering both the accuracy of predictions and the balance between false positives and false negatives. Calibration metrics like ECE and MCE assess the quality of the confidence levels.
What are the key takeaways from this research and what are the potential future directions?
This research demonstrates a promising approach to onboard FDD for Space Launcher Engine electrical systems. The framework's flexibility and use of calibrated classifiers provide a robust and reliable solution. Future work will focus on validation with real-world data and exploring techniques to improve robustness to prevalence shifts such as conformal prediction. Further investigation into the impact of different window sizes and the optimization of CRSM parameters is also warranted.
The authors mentioned the use of PCA, TSNE, and UMAP for data analysis. What role did these dimensionality reduction techniques play in their research?
These techniques were used to visualize the high-dimensional data and assess the degree of class overlap between different fault classes. This helped to identify which fault cases were easily separable and which presented greater challenges due to significant overlap. This information guided the selection of fault classes for the main evaluation.
The paper highlights the importance of balancing the trade-offs between false positives and false negatives. How did the authors approach this in their model development?
The authors carefully considered the cost implications of both false positives and false negatives. They used techniques like threshold moving and QSCM to control the false positive rate while maintaining acceptable recall. The choice of thresholds and USM parameters was based on experimental evaluation and a consideration of the relative cost of different types of errors.
The paper mentions the use of a validation set for calibration. Why is it important to use a separate data set for calibration rather than using the training data?
Using the training data for calibration would lead to an overly optimistic assessment of the model's calibration performance. A separate validation set provides an unbiased estimate of how well the calibrated probabilities reflect the true class probabilities. This ensures that the calibration is generalizable to unseen data.
The authors use a combination of techniques to improve the reliability of their predictions. How do these techniques complement each other?
The TCAE provides effective feature extraction, the HGBT classifiers offer robust classification, calibration ensures accurate confidence levels, CUSEM reduces false positive, and conformal prediction handles UDI data. These techniques work together to create a comprehensive and reliable FDD system.
The paper mentions the use of different calibration methods such as plant scaling and isotonic regression. What are the differences between these methods and why did the authors choose isotonic regression?
Plat scaling is a parametric method that assumes a sigmoid relationship between scores and probabilities, while isotonic regression is non-parametric and allows for more flexible relationships. The authors chose isotonic regression because it provided better calibration performance in their experiments, particularly for the binary classifier.
The results show that the model generalizes reasonably well to the test 2 dataset, but there is a noticeable increase in the false positive rate. What are the potential reasons for this?
The increase in the false positive rate in the test 2 dataset is likely due to the significant prevalence shift between the training data and the test 2 data. The model was trained on a dataset with a high prevalence of fault cases, but test 2 has a much lower prevalence. This can lead to the model being overly sensitive to potential faults, resulting in more false positives.
This has been a thorough discussion of the paper. Thank you.